Good morning, good afternoon, and good evening, everybody. Today I will be presenting on the microfluidic immunodiagnostic assay device used in my practical, its working principle, and how it relates to COVID-19 antigen rapid test, also known as ART. Firstly, this device is a microfluidic assay chip. Microfluidics is the science and technology of handling very small volumes of liquid in channels with dimensions in the micrometer range. At this small scale, the flow is usually laminar, meaning the liquid moves smoothly through the channels instead of mixing turbulently. Surface tension and capillary effects also become more important, allowing liquid to move through small channels without complex external pumps. This makes microfluidic devices useful for point-of-care testing, where tests can be done quickly and near the patient instead of only in a laboratory. The device contains different functional parts. The white chip is the reagent deposit, which contains sodium carbonate, an alkaline substance, while the red chip acts as the indicator reagent. When citric acid was introduced, it flowed through the channel and reacted with the sodium carbonate. Although an acid was added, the final mixture remained alkaline because there was sufficient sodium carbonate to neutralize the acid. Since excess sodium carbonate remained after the reaction, the pH stayed above 7. As a result, the red litmus paper turned blue, showing that the liquid had successfully moved through the microchannel and interacted with the reagent system. The small side tubes act as air vents, allowing trapped air to escape and preventing bubbles from blocking the flow. The working principle of this assay is based on controlled movement of liquid through microchannels, followed by a visible chemical reaction. When the sample is introduced, it travels through the channel by capillary-driven flow. As it reaches the reagent deposit, the sodium carbonate can dissolve and interact with the incoming solution. If the sample is acidic, the pH change affects the indicator, causing a visible color change from red to blue in part of the detection region. This gives a simple visual result, similar to how many rapid tests rely on a visible signal rather than a complicated instrument. This device can also be linked to the concept of lab-on-a-chip technology. A lab integrates one or more laboratory functions into a small device, reducing reagent volume, sample volume, cost, and testing time. Microfluidics is useful for diagnostic applications and point-of-care testing because it supports miniaturized and rapid testing systems. Although my device uses an acid-base reaction and in the color change, it is related to COVID-19 ART because both use the same general idea of a rapid microfluidic or lateral flow assay. In a COVID-19 ART, the sample is usually taken from a nasal swab. The test detects viral antigen proteins such as proteins from SARS-CoV-2 using specific antigen-antibody binding. Immunoassays are based on highly specific binding between an antigen and an antibody. In a typical sandwich immunoassay, the target analyte binds to one antibody, then another labeled antibody binds to it and generates a visible signal. For T devices, the reagents are pre-stored in dried form on the test strip. When the liquid sample is added, capillary force pulls it through the device. The liquid redissolves the dried reagents, allowing the target viral antigen to bind with antibodies and produce a colored line at the test region. This is similar to my device because both systems store reagents on the chip, use small channels or porous pathways to guide liquid movement, and produce a visible color-based result. For COVID-19 testing, PCR detects viral RNA and is more sensitive, but it requires more equipment and laboratory processing. ART detects viral antigen proteins using immunoassay principles. ART kits are a viral antigen immunoassay that is lower cost, frequently used, and suitable as a preliminary test. In conclusion, the device from my practical demonstrates the basic ideas behind rapid diagnostic devices. It uses microfluidic flow, reagent deposits, air vents, and a visible indicator reaction to show how a sample can be transported and detected on a small chip. While it does not detect SARS-CoV-2 directly, it models important features of COVID-19, especially reagent storage, capillary flow, and visual signal generation. Therefore, this device helps us understand how rapid point-of-care diagnostic tests are designed and how they can provide fast, simple, and low-cost results. Thank you so much for watching.